All right, so in this set of notes, we are going to be learning about not only trigonometric limits like the title of the note suggests, but if you look at the objectives, we're also going to be learning about something called the squeeze theorem. And then in addition to that, some ways to evaluate trigonometric limits. So I'm going to read the paragraph that I have written at the beginning. When trying to find the limit of a function that could be particularly difficult to find, the squeeze theorem may be used to confirm the limit of a function via comparison with two other functions whose limits are known or are easily computed. So there are definitely some functions that we could have some difficulty with. And numerically evaluating a limit is not a convincing technique. We want to be able to show a very convincing reason for why a limit value exists. When we are plugging values in from either side of a value that we're approaching, that's just you approximating the limit. The squeeze theorem is a way to prove that the limit is exactly the value that you say it is, not that it looks like it's approaching something. So let me say that it looks like this. Now, I will also say one more thing. The squeeze theorem is a last ditch resort. This is not the first technique that you want to use every single time that you evaluate a limit. If you can use direct substitution, i.e. just plug the x value into the function, do it. If you can algebraically simplify a function, so like factoring and canceling, multiplying by the conjugate, rewriting your trig functions. If you can algebraically manipulate the function and then do direct substitution, yay, great, that's preferable. Squeeze theorem is a last-ditch resort if you can't do those things before this. So let me go over what the squeeze theorem says. It says, consider the function f of x that is trapped between two functions, u of x and L of x, on the interval a to b. I'm going to stop here for a second. This is just basically saying that our function is in between two other functions. It does not always need to be between those two functions. It just needs to be trapped between those functions over some interval that has the x value c in it. And I have u of x and L of x used specifically to show that u of x is the upper function, L of x is the lower function, and that f of x is just between them on some interval with c in there. So the squeeze theorem, and I'm going to write that criteria up, says that if f of x is between, and it could equal the other two, that's fine. It doesn't necessarily have to, but it, at the very least, it's between L of x and u of x for all x values contained within a to b. And here's the other part. So that's just the trapping portion. Here's the squeezing portion. If the limit as x approaches c of your upper function is also the same as the limit as x approaches c of your lower function, and let's say that that value is L, then we can conclude that the limit of our function itself is the same as those two other limits, L. So we have two criteria that we need to ensure. Is our function trapped between two functions? And do the limits of the upper and lower function equal the same thing? If we can meet those two criteria, then we can state our conclusion using the squeeze theorem. And one thing that I would like to note that I have written below this, the squeeze theorem can also be applied to one-sided limits. That is perfectly okay. It doesn't necessarily need to be overall limits. You can do the same thing with one-sided limits. And I will also say C could technically be one of the endpoints as well. Okay, so let's get into our first example using the squeeze theorem. And note, I will always specify if we are going to be using the squeeze theorem. I will not give you evaluate this limit and not specify that I want you to use squeeze theorem. If it's not specified, then you're probably going to be using some other technique. All right. So in example 1, it says evaluate the limit of x sine of 1 over x as x approaches 0 using the squeeze theorem. Can anyone tell me why this might be a particularly difficult function to evaluate otherwise? Hopefully you said that because there's division by 0 inside of sine, making the inside of sine undefined. So what I would like to start off with doing is graphing what x sine of 1 over x looks like. That way we can try to come up with some functions that might trap this function. Now, before I even plot this, there are two ways that you can go about trying to find an upper and a lower function that would trap the function of interest. You could just do guess and check, which for some of the homework problems, you are probably just going to want to do guess and check. Pick a function that you think might trap it, check to see if it actually does over the interval of interest. The other way, you can be a little dynamic about this, and I will show you how to be dynamic on this first one. We're not going to keep being dynamic for the rest of them. We'll do a guess and check for the next one. Okay, so it looks a little crazy as I get close to 0, which as expected should happen because we had division by 0 as we approach 0. So I'm just going to zoom in a little bit closer to the x equals 0 portion. So zoom 6. And again, if you notice, I have my little cursor down here. There's the key history at the bottom. So I'm going to zoom in. Oh, I'm sorry. I need to do that one more time. I did zoom standard. Zoom in and zoom to. And I have that blinking cursor in the center. I'm going to click on that because that is actually where I want to zoom in. Let me zoom in one more time. I want to really try to see if I can see what's going on here a little bit better. Ooh, okay, that looks really good. So if I kind of look at this function, there's definitely some functions that I might be able to choose to be above and below it. I'd like you to write one or two down that you think might actually work. And then we'll take a look here in a second and see if it actually does work. So pause the video, try to write a few functions that you think might trap f of x above and below just around x equals 0. It doesn't need to be forever. And hopefully you've unpaused the video now. I'm going to show you a way that you can dynamically try to figure this out. So I'm going to write my function, well, part of my function down. Instead of writing it down, I think I'm actually going to just look at the graph of our most basic function here. So we have x times sine of 1 over x. If I strip that down to just sine of x, the most basic function that is a part of this entire thing. I see that sine of x itself is trapped between -1 and 1 always. Those are the outputs that it will always be between. And in fact, even if I have 1 over x as the inside of sine, it's still going to be trapped between those. So if I'm just looking at sine of 1 over x, I could use an upper function of 1 and a lower function of -1. And it is equal to 1 at one point and -1. But the difference between sine of 1 over x and the actual function that we're looking at is that it's multiplied by x. So if I multiply every interval here by x, oops. Let's see if that statement still holds. And yes, I'm using Desmos just for ease of this for now. Okay, let's see. Let's make that an X and a negative X. Ooh, okay. So, oh, and I needed to make that an X. So it doesn't look completely like what we want. It looks like our negative X function is above, but only on the left side of 0, because on the right side of 0, it goes below our function. And same thing with X. It switches order with our upper function on the opposite side of 0. But if we notice, it kind of looks like if we use the absolute value function, we would stay above f of x the entire time and below f of x the entire time. And there we go. So that's kind of dynamically how we could end up building up to having a good upper and lower function. Sometimes it's a little bit more complicated, sometimes it's not. So basically we started with, I know that sine of x is always between -1 and 1, and so is sine of 1 over x. The difference between the functions is that if I multiply by x, I could get negative x is between negative x and, I'm sorry, sine of 1 over x is between negative x and x. We verified that and saw that we just had to make one modification by making it the absolute value signs. Now, this is only part of our first criteria. We also need to figure out an interval where this is true that includes 0. So it looks like every value that we have on the screen, the upper function's above, the lower function's below. It might actually be the case for all real numbers, so let's see. Yeah, I would think that we could just use all real numbers as our interval. Now, if you don't trust that it's all real numbers, then pick an interval around 0 that you can say for certain the upper function's above and the lower function's below, like from -0.5 to +0.5. That would work. I'm just going to say for all real numbers. So this is our first criteria. Second criteria, we need to check the limits of our upper and lower function. What does that limit equal? Hopefully we said 0. And the limit of our upper function? Also equals 0. So both our first and second criteria are satisfied. We can go ahead and write up our squeeze theorem sentence here. Now there's a lot that you have to write because anytime you're using a theorem, we need to write our statement in sentence form. All right, you ready? I'm going to write a general paragraph for you with fill in the blanks. I want you to write that down for both this problem and the next one, since we are using squeeze theorem for both. And I might need to respace this. So I'm going to pause the screen and the stuff will appear in 3, 2, 1. So you can go ahead and write this sentence in both this example and towards the end of the next example. The blanks are basically for our criteria. So since first criteria is met and second criteria is met, we can say whatever the conclusion is by the squeeze theorem. So I want you to pause the video now. Once you're, well, pause it now, continue writing the sentence, and I want you to fill in the blanks. Welcome back. Hopefully you have it filled out. So here's what I am going to write in the blanks. If you need to fix things, go for it. Since L of x equals negative absolute value of x is less than or equal to x sine of 1 over x is less than or equal to u of x equals absolute value of x for all x and then real numbers, or whatever interval you said. Now, you don't necessarily need to write L of x and U of x, but believe me when I tell you, it gets really annoying to write each function over and over again. So if I just have to say L of x later on versus negative absolute value of x, which is not too bad here, but some of the functions can get pretty big, I'd prefer to call L of x versus the entire function. You can do the same thing if you wanted to write f of x for the middle function. And next criteria, the limit as x approaches 0 of negative absolute value of x equals the limit as, oh, I thought I was going to call L of x. Now, if I just said negative absolute value of x the entire time, I don't need to write L of x in there. Here we go. And both of those limits equal 0. We can say that the limit as x approaches 0, and since I didn't label it f of x, I actually have to say the function in the first place, equals 0 by the squeeze theorem. If you have any questions, make sure you write them down. So in the next one, you're also going to evaluate that using the squeeze theorem. I did say that for that one, we are going to have to get guess and checky, because if you think about it, the way that we built up from the last one, I did -1 is less than or equal to sine of x is less than or equal to 1. And in this one, we have division by 0. I don't really think it works if we do -1 over x is less than blah, 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 blah. You could try it out, but I think that you would probably prefer to pick out two functions that actually look like it's squeezing and trapping this function just by doing some guess and check. So pause the video. I want you to play around with some functions that look like they will trap and squeeze sine of x over x. Ooh, definitely need to zoom out. Okay. Now, if you wanted to zoom a little bit in, you can. There we go. Okay. So I'm curious to see what functions you guys chose. Personally, I'm going to be using y equals 1 because that is definitely above my function, but it also touches my function around x equals 0. So I'll use 1 as my upper function. And then I think for my lower function, I might use a quadratic, but it's going to have to be flipped upside down, so a negative quadratic. But if I had a negative quadratic, it would follow this path. So I need to have it shifted up 1. So this is literally just because I've already spent time with this, but expect that when you are trying to find an upper and lower function through a guess and check technique, you might play around a little bit. It might be an absolute value function if it needs to be a little bit tighter of a turnaround, maybe a quadratic function if your function looks a little bit curvier around where you're approaching, or maybe another trig function might work. I mean, it really could here. So to me, it looks around this point, and maybe I'd have to zoom in a little bit more, but I'm thinking I'm pretty safe here, that 1 stays above my graph for a while, and then the negative x squared plus 1 also stays below it for a little while. I don't feel like zooming out, so instead of zooming out just to see if it's all real numbers, I'm just going to say between -1 and +1, my upper and lower function are definitely above and below f of x. All right, so we'll start off with L of x equaling negative x squared plus 1, which is less than or equal to, ooh, theta is my variable, so I need to use theta here. And if you don't like using theta, you can switch everything to x's instead. And I said that I'm gonna go around -1 to 1, because I don't feel like zooming out to see if it's all real numbers. And then I picked those functions not only because the upper and lower functions trapped sine of theta over theta, but they also touched / squeezed my function around x equals 0 or theta equals 0. So the limit as theta approaches 0 for L of theta would be, see if I plug 0 in, 0, -0 squared is still 0, plus 1 is 1. And that is also the same value for my limit as theta approaches 0 of u of x, for u of theta. So the limit of a constant is that constant. Right. So because my function is trapped between L of theta and u of theta, and the limits of them as theta approaches 0 are both the same thing, we can say that the limit of sine of theta over theta as theta approaches 0 is 1 by the squeeze theorem. Now there's one more thing that I want to do before we move on to the important trig limits, because these are our notes and we did a lot of stuff in the calculator. I also want to draw visuals of the graphs for both of these examples. So since I'm already on example 2, I'm going to draw my function along with the upper and lower graphs. Use whichever graphs or whichever functions you did to graph. I'm going to put my main function in pink. That's about what it looked like. I will do my lower function in, let's see, what color should I have in front, just to be consistent. Red and green. And then my lower one. Okay, I'm going to do the same thing for example 1. I'm going to draw the upper and lower functions first. So we had absolute value. Oops. Of x. We had the negative absolute value of x. And then we have the function in the middle, which if we had paid attention, kind of looked like this. Something like that. Okay, so let's move on to the important trig limits. We just learned one of them, that the limit of sine of theta over theta as theta approaches 0 is 1. And if you'd rather write that with x's, you can do that. In fact, I think I might prefer to write that with x. So the limit of sine of x over x as x approaches 0 is 1. So if you notice that when you are evaluating limits and you are trying to algebraically manipulate it, you notice that you can break it up into sine of x over x times something else or plus something else. You can use your limit laws to break it up into separate limits. And this could be the value of that part of the limit. The other one, which we can write it in 2 different ways. It's the limit as x approaches 0. Still dividing by x, but we have a longer expression in the numerator. It'd be 1 minus cosine x. And that would also equal, oh, I'm sorry, that equals 0. The other way that you could write it is with the numerator in the opposite order. And because the limit still equals 0, it doesn't really matter. So the one with sine is 1, the one with cosine is 0. Let's go ahead and move on to our next example. And notice in the next example, it does not say to evaluate it using squeeze theorem. So my expectations when I don't specify squeeze theorem is that you can either do direct substitution or you could use algebraic manipulation if it's not able to be directly substituted. I'm going to plug this in off to the side to see if I'm getting a value that I could just do direct substitution with. And if not, then that tells me I need to manipulate it a little bit. Oh, well, that was pretty silly on my part. I didn't even look at the problem. You cannot directly plug 0 in because then we get division by 0, and that is a problem. So what this tells me is that I need to do some algebraic manipulation. But remember, something like this, if you were to write this on the AP exam, you would need to cross it out because you saying that you can divide by 0 is not okay. I want to see that you kind of tried to do that in the first place, but I still want to see you crossing it out. All right, so let's try to algebraically manipulate this. And remember, when we see trig, the best thing that you could start off with doing is rewriting everything in terms of sine and cosine. All right, so look at that, take a little moment to think about what we could do from here to make this look a little less complicated. I mean, obviously we're making it look more complicated even in this first step, but what's something that we might be able to do now to make it look a little bit better? Hopefully you notice that we have a fraction getting subtracted by something in the numerator. So what we could do is try to get a common denominator so we can actually subtract 1 over cosine by 1. Now, in order to get this to have a common denominator, we're going to have to multiply 1 by cosine over cosine. So then we get 1 over cosine minus cosine over cosine, which is really 1 minus cosine over cosine. Ew, we have a 3-part fraction. Think about how we might be able to break this up and write it a little nicer. Hopefully you said something along the lines of keep, change, flip. Or multiply by the reciprocal. So I'm going to keep my fraction from the numerator. But then instead of dividing by theta, I'm going to multiply by 1 over theta. I see something that we might be able to use. Why don't you guys look back at your important trig limits? Do you see how we have basically this as a part of our limit? There's some extra stuff, but I see a 1 minus cosine theta over theta, and we have the x value approaching the same thing. So I'm going to rewrite this as the product of the 2 limits, where I have 1 minus cosine theta over theta in one limit. And then in the other limit, whatever is remaining. So we would have remaining 1 in the numerator and then a cosine theta in the denominator. Now, before I decide to continue, I need to double check, do these limits both exist? Because if either doesn't exist, I'm not allowed to break them up using the limit laws. So I know the first limit exists because that's one of our important trig limits. Does the second one exist? If I plug 0 in, is that going to be okay? It is. So I know the first limit gets me 0. And then if I were to do 1 over cosine of 0, that is, cosine of 0 is 1. So I'm just doing 0 times 1, which is still 0. Okay. Let's move on to our last topic in the notes, evaluating a limit by changing variables. So what these are helpful for are basically if we have something other than just a plain x or a plain theta inside of our trig limit, we can use some substitution or we can do something slightly different. So I'm going to show you 2 ways that we could do example 4. Do you notice how the inside of that is not just a plain h? So you have 2 options. I'm actually going to go with option 2 first and foremost. This I think might be a little bit easier to deal with. So the second option says multiply the numerator and denominator by the constant that's inside of the trig function. Regardless of the method, we're still going to use the limit laws and important trig limits to finish evaluating this. So if I go with option 2, I'm going to start by writing my limit in the first place. And I'm going to multiply by the constant that I have, or the coefficient that I have inside of my trig limit. So times 4 times 4. So that becomes the limit as h approaches 0 of 4 times sine of 4h over 4h. Now, do you notice that if this wasn't there, I have one of my important trig limits? It's okay that it doesn't say 4h approaching 0. It's just the variable portion that really matters. So what I can do here is use my basic limit law, that constant multiple, and move that coefficient of 4 out front. And the reason I have to do that is because I know the value of the important trig limit. I can't have other things inside of it before I evaluate. It has to be just that plain important trig limit. So really, this is 4 times the limit of sine of 4h over 4h as h approaches 0 is 1. And 4 times 1 is 4. This, I think, is the preferable way to do things. I will show you option 1, though, which uses substitution. And if you already decide that you like option 2 better, go ahead, skip this, go to the next example. So option 2 uses substitution. So in my next line, I'm going to say, let the expression that's inside of sine, so let 4h equal theta, which means that theta over 4 also equals h. And I'm going to do some substitution with that in my next limit. So instead of h there, I'm going to have theta over 4 approaching 0. And then in my numerator, sine of 4h actually becomes sine of theta. And then in my denominator, instead of h, I have theta over 4. We are going to do some simplifying. Theta over 4 approaching 0 is still going to be theta approaching 0. If I kind of treat that like an equation, if I multiply both sides by 4, theta still approaches 0. And then I have in my denominator division by 4. That is the same thing as multiplying the entire fraction by 4. But instead of having the 4 on the inside, I will multiply it to the outside using that constant multiple limit law. And through a different technique, I still get 4 times 1, which is 4. The substitution technique you will have to use regardless sometimes, but I think if you can manipulate it to end up just multiplying the numerator and denominator by the coefficient that's on the inside, like we did in option 2, that could be preferable. All right, let's flip it to the very last example. I want you to go ahead and try that one on your own. So pause the video, and then when you're done, unpause it. I'm going to start solving it now. So option 2 last time showed us that you would multiply by the coefficient that's on the inside of the trig function. We don't have anything other than a 1 there. So you might have noticed, how could I deal with the 5 in the denominator? It's just a multiple. It's just a scalar here. We can move that scalar in front of our limit. But because it was in the denominator, it has to stay in the denominator. Which means we have a 1 in the numerator. So it's basically like we multiplied sine of h over h by 1/5. I know the limit value. So it's 1/5 times 1, which gives me an overall limit of 1/5. And we are done with the notes. If you have questions, make sure you ask during class. Otherwise, practice soon to come.